Hello everybody, welcome to this video where we're going to reprove that the real numbers are uncountable by using the very classic proof due to Cantor in 1891, and this today is sometimes called Cantor's diagonalization argument. So the first thing we're going to do is actually go back to our uncountability omnibus theorem where we said actually the real numbers are in bijection to any finite interval on the real number line. So in particular, the cardinality of the interval from 0 to 1 is actually equal to the cardinality of the real numbers. So if we can show that the cardinality of the interval 0 to 1 is uncountable, all right, it's uncountably infinite, then the real numbers have to be uncountably infinite. Incidentally, right, to show this, right, we had to write down a bijection, and actually, if we wrote down the function cotangent of pi x, this ended up being a bijection from the unit interval to the real numbers. Okay, so that's how we justified this cardinality statement. Okay, so this gives us our theorem from which it will follow that the real numbers are uncountable. So the theorem is that the unit interval is uncountable. Okay, so note if we are already using the previous result that, oh, we know 0, 1 is in bijection to R and R is uncountable, then this is obvious. But we want to prove this independent of knowing that R is uncountable. Okay, so in words, right, the statement is there is no bijection from the set of positive integers to the unit interval 0 to 1. All right, so just as before, this proof is going to be by contradiction. And there's a nice picture that we're going to write down, but let's start by setting things up. So we're going to assume that we do have a bijection. So assume f is a bijection from the positive integers to the unit interval. Okay, so that means that we can order the elements in the unit interval 0 to 1, right? Nice. So that means that I can write down like the nth one, right? So I can write down f of n. And what is it? Well, it's some element from 0, 1. Well, it has a decimal expansion then. It's going to look like 0 point. Okay, well, there's like the first term, and we're going to write it as like dn1. And then the second will be dn2, and then dn3, right? D for digit. Okay, so this is the first digit in the decimal expansion corresponding to the number n. And of course, this just keeps on going, right? Forever and ever. Okay, of course, they all could be zeros at some point. That's fine. All right, they could all repeat, but they're just going to go on and on. Now, we know that f is a bijection, and hence it's surjective. And so every real number has to be in the image of f, meaning it has to have a preimage. Okay, so since f is surjective, if x is in the interval 0, 1, then there exists some m in the positive integers such that f of m is equal to x. Okay, fine. That's just the way it goes. But I want to write down a special number that I claim cannot be in the image of f. All right? So let's consider x. Well, if it's some number between 0 and 1, it has a decimal expansion. So I'm going to write down the following decimal expansion: E1, E2, E3, E4. Okay. And it keeps going. Fine. I need to tell you what these e's are, right? So, because this is a specific number. So, where, if I go and look at the ejth term, right? So maybe this is the third term. I'm going to make it equal to the number 5 if, when I go up and look at f of j, so what is f of j going to look like? So f of j will be 0.dj1, dj2, dj3, etc. And at some point I get djj. Okay? And of course it'll keep going, dj, j plus 1, and so forth. But I want to focus specifically on this djj. And if this djj in the expansion for f of j is not equal to 5, then I will make my ej equal to 5. Okay, so that's how I do it. When I get to the 5th position, I'm going to look at f of 5. I'm going to go to the 5th position in f of 5, so I'll look at d55, and I'm going to ask, does d55 equal 5? Yes? No? Okay, well, if it's no, I'm going to let my ej equal 5. Okay, and what if djj does equal 5? Well, if it was equal to 5, then I'm going to let my ej be 6. So this number x consists entirely of 5s and 6s in the decimal expansion. All right? And what I claim is that amazingly, this x cannot possibly be in the image of f. Okay, so this is very strange. Now let's just draw the picture quickly to see where is this idea coming from? Why is this called Cantor's diagonalization? Okay, so when I'm looking at these f's for the different ends, okay, I could write 1, 2, 3, 4, 5, 6, and so forth. I can go out a certain number of places, right? The first decimal place, second, third, fourth, fifth, sixth, and so on. So in this first position here, I could look at D11. That would be the first decimal place for f of 1. And then over here, I could look at D12, the second decimal place for f of 1. And D13 and D14 and so forth. And now I come down here and I say, okay, look at the first decimal place for f of 2, and the second decimal place for f of 2, and the third decimal place for f of 2, and so forth. And the idea here, when I defined this x, is I'm only going to look at these elements which show up on the diagonal of this chart. And those are the ones that are going to determine what's happening. And the beauty here is that because I'm choosing on the diagonal, I'm getting exactly one entry from each integer. I'm also getting exactly one entry from each place, right? First decimal place, second decimal place, third decimal place. Okay. There's nothing that would stop me from kind of doing this in reverse order, but this is just sort of the cleanest way to write it down. Okay. Now, that's where it's coming from. This is why it's Cantor's diagonalization argument. Okay, and we're going to actually use this a bunch. But I said I claim x cannot be in the image, right? Well, if it is in the image of f, right, then it has a pre-image, call it m. So we know that x is equal to f of m. Okay, so what do I know about dmm? Well, because x is equal to f of m, and what is f of m, right? Well, f of m is 0.dm1, dm2, dmm, continue on. So dmm is the mth position in f of m, but f of m is equal to x. So dmm is in the mth position in the expansion for x. But we also know that the expansion for x looks like this, 0.e1, e2, e3, etc. And at some point you get to the mth position and you get em. And so em and dmm are in the same position, and so they have to be the same value. So dmm is equal to em. But look at what we have up above. You take any j, right? J could be m. It's different than the corresponding d. EM and DMM are not the same. Go down here. EM and DMM are not the same. So this is a contradiction. Right? Since they're always different. Where did this contradiction come from? Well, it came from this understanding, well, look, X is in the image, which came from F being surjective, which came from F being a bijection. Therefore, F is not a bijection, and so 0, 1 is uncountable. Oh, that's so clean, so slick, just out of nowhere, right? Okay, we're going to redo this proof, okay, but with a different theorem. Okay, but you're going to see the proof is going to work very, very similarly. Okay, so in our uncountability omnibus theorem, right, we had this result, okay, which said that I'll abbreviate it here. So if you had A1 through A2, A3, etc., are sets with at least 2 elements. Okay, then the claim is that if I look at the Cartesian product, which I could abbreviate like this, that this is uncountable. Okay, so even if they're all finite and they just have 2 elements, then it's true that this infinite Cartesian product is actually going to be uncountable. Okay, so let's do a proof of that. Okay, so we didn't prove that in the other video. All right, so first, I mean, this is not going to catch you by surprise here, but I claim that this thing is not finite, right? Well, we'll make that clear. So how do we do that carefully? Well, first, we know that each of these has at least 2 elements. So choose 2 specific, these are distinct elements, from each AN. Okay, let's call them DN1 and DN2. Okay, so I'm going to always use a superscript here so that we know which set it's coming from. Okay, so I claim we can now write down an infinite number of elements. And the way we do it is by doing these. We say, okay, here's one. We're going to do DN1, N1, D11, D21, D31. Okay, and at some point, I'm going to have an mth term and I'm going to put down 2. Okay, but all the other ones, so this next one, right, would be dm plus 1. That'll be back to a 1. dm plus 2. That'll be back to a 1, and so forth. Okay, so there's going to be one position where I put in the second element that I've chosen from the set, and all the other positions I put in the first element. Well, there's an infinite number of ways of doing this, right? I could put this m can be chosen for any positive integer. Okay, so all of these, right? So here m, so if I take the set of all of these where m is some positive integer, then this set, right? This set is infinite. In fact, there's a bijection with the with the positive integers here. Okay, so this implies that if I take this Cartesian product, this is infinite. Okay, so it's not a finite set. Now, what if it was countable, right? Because we really want to claim that it's uncountable, but what if it was countable? So if this Cartesian product is countable, well then of course we get a bijection, right? Between the positive integers and this Cartesian product. So let's call it G, since we used F in the last one. So there exists some G, which is a bijection from the positive integers to this infinite Cartesian product. Okay, so because I have this bijection now, it means that for any element in the positive integers, I'm going to get some particular element from this Cartesian product. All right, so for every, say, n in the positive integers, we obtain an element g of n, which is going to look like a sub n1, a sub n2, a sub n3, and so forth. Okay, so the superscript again telling you it's coming from first, second, or third, whatever component, and then the n is just referring to this n we get. Okay, we don't have any particular order that we know on these a sub n's. Okay, and this is, of course, an element of the Cartesian product. Okay, oh, maybe I should use a different letter here. Let's call this now k, since I'm using an n over there. Okay, fine. On the other hand, because G is a surjective map, I know that every element of the Cartesian product is in the image of G, right? It has some pre-image. So if I have some element, I can write it down in this way. Okay, fine. So let's take some element. All right. So let's let A be given by the following element. It's going to have an E1, an E2, an E3, and so forth. And this is going to be some element in the Cartesian product. And again, I'll switch over to the K notation. Okay, and what are these E's going to be? Okay, so this should remind you of what we did in the proof that 0, 1 was uncountable. We built a decimal expansion by defining some E's. Hey, that's what we're doing here. And somehow based on like some diagonal elements. Okay, so let's see how that's going to show up. Fine. So I'm going to define E sub n to equal, well, okay, remember, I have two specific elements, right? dn1 and dn2 for each n, right? And this is kind of like choosing the numbers 5 and 6, right? I had these two elements. Okay, so I'm going to let en be dn1, but only if, well, okay, if I write down g of n, what is g of n? Well, actually, we already wrote it down. There's g of n. Okay, and I can look now at the nth position. Okay, and that'll be ann. So I can ask, what is ann? Is ann equal to dn1? And if the answer is no, it's not, then I'm going to make my en, I'm going to make it equal to dn1. And what if ann does equal dn1? Well, in that specific case, then I'm going to make my en equal to dn2. Okay, so you see it's very important that we know we have at least two elements so that we can play this trick. Okay, and now it's going to work the same as before, right? Because A is an element of the Cartesian product, it has a preimage. So since A is in the Cartesian product, again, we'll use the K's here. There exists some preimage, okay? So it's going to be some element of the positive integers such that G of M is equal to A. Okay, but what was G of M? G of M is equal to A1M, A2M, A3M, etc. But A is equal to E1, E2, E3, etc. So let's take a look now at the mth position in A. So the mth position is going to be, out here, right? That'll be EM. So I have the mth position. It has to equal the mth position in G of M, right? Okay, go out here. What's the mth position? It's it's AMM. So EM has to equal AMM. But what did we see up above? We saw that when EN is equal to DN1, ANN is not equal to DN1. So in this case, the EN and the ANN are not the same thing. And over here, when EN is DN2, the ANN is not equal to DN2. It's equal to DN1. And again, the en and the ann are not the same. And this was true for all n. So this means that this cannot happen. This is a contradiction. Okay, so this is almost exactly the same proof as we used to show that 0, 1 is not countable. Okay, and it's again a diagonalization argument. Okay, so you say, okay, let's put down here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. What are we counting? Well, there's the natural numbers, and then there's the position in this list that we make. All right, so we get A11, A12, A13, A14, etc. And I get down here A21, A22, A23, so forth. And what I'm doing is looking again at these diagonal elements and using those, right? I just check, do they equal dn1 or dn2? Or not, right? dn1 or not. And if they do, then I make my en equal to dn2, and if they don't, I make my en equal to dn1. All right, so I'm just checking this diagonal, and that allows me to build a number or an element that doesn't appear anywhere in this set, which is, again, really cool. So we conclude that this Cartesian product is uncountable. And there we go. All right, we'll see you next time.